Swayam Prabha. Digital India. Educated India.
We are going through very important topics now, which pave the way for our rigid body kinematics. So one of it is a very important one, which is the rotating frame. So the translating frames are easy to understand. So if there is a frame which is translating with respect to, say, another fixed frame, so what all we need to do is that whatever observations you make regarding velocity and accelerations, so in the moving frame, so you have to add the velocity of the origin as well as or the accelerations of the origin, so that you can get the velocity and accelerations with respect to the fixed frame respectively. So that is that's pretty straightforward, not too much to worry about, because the ij remain parallel to the fixed frame, so they don't have any derivatives. But however, the one which we have been discussing in the last couple of classes are very important, that if we have a rotating frame, how the observations are related. The observations which are made in the rotating frame without knowing that you are rotating, and how they can be related to the fixed frame. So this is the one which we have been looking at. And towards the end, going a little slow, I'll also take a few small examples which you can appreciate and understand, which, as I say, which have a lot of bearing on our kinematics of rigid bodies later. So please try to understand, pay attention. If you have any difficulty, you can call, or you can ask me or ask any of the tutors. So just to go back a little bit, let me change the nomenclature a little bit. Earlier I was using xy and x prime, y prime. Now let's do that as xy, y, big xy and small xy. So it's easy to say. Okay. So now so these are various things. The position vector that's measured in the small xy frame is like this, and that is measured with rxy is like this. And then we went through, this is what I was saying. This is general. This is the general thing. And then after this, here, this is So this is the general relationship in the sense that translating, let's rotate. This is what I said. If O prime is translating, in the sense that if it is like this, so then what all you need to do is that you have to add whatever observation you make with x prime y prime, you have to add that. In addition to that, this xy is also rotating, in which case we said that we have p here. So this position vector is observed in big xy or small xy. As such, they are same. But however, the things will get more involved when you have the velocities. So the velocities here it's like this. So this is what it is. The time derivative with respect to the fixed frame is the time derivative as seen in the rotating frame plus a correction term omega cross r here. And the same thing, this is with respect to the velocities, which is okay. So this position vector r is like this. So maybe you can either use it or with substitutes big xy or small xy. So I'll just leave it at this moment. And then we went on to do this in y is d dt of v y. So which converted to, we went through the whole exercise. Okay, so this is the absolute acceleration with respect to the fixed frame is nothing but the acceleration of the point P as observed in the small xy without any field part that you're rotating. To that, we had a omega square r. Okay, so since you do not know, this is very clear to understand. So this is nothing but a centripetal acceleration of P because the whole frame is rotating about O, right? And then this is alpha k cross r. So this is nothing but a angular acceleration of the frame k cross r. You know very well that it is. So these two are, I'll explain these things still further. So it is omega cross r with a negative sign goes towards like this, and alpha k cross r is the perpendicular to this vector, and it is in this direction, assuming that alpha is positive or counterclockwise. And if it is clockwise, then it comes down. So apart from that, I'm sorry, this is V. So then this is the last term, which we said is the Coriolis component. And we tried to explain why this has come. What is that which we missed? There are two things that has been missed here. Is that as the point P is moving, then its rotational velocity is changing. That's number one. And the other one is another component where this velocity Vxy is changing its direction because of omega. Okay. There are two components which I'll just explain. I explained it last time, but I'll explain it again because this is a very important term for not only now, but in future, very important. Okay. So let us try to understand this with respect to a very small problem. A very small problem here is let's assume that there is a rod here, which is on which we have a bead, which is moving along the rod. So this of course can be done very easily using the polar coordinates also, but let's try to understand from this, which is complex, but then it will make you understand new concepts. So for that, what we do is that this rotation is absorbed in the frame itself. So in the frame is rotating at the speed of omega and maybe alpha, right? So that means that this bead is always on the x-axis. It is just moving along this axis with a certain velocity v, as well as maybe some acceleration a, and we say that vxy, small xy, and axy, right? So that's what we say here. So this has two terms, v a, and we put the subscript small xy because these are observed. We assume that it is moving only along x-axis and while the frame itself is rotating. Okay, so this is what is the picture. And then now if we try to understand what are the absolute velocities with respect to big xy, fixed frame, so that's easy to understand. So for example, the formula here is that Vxy is nothing but V as observed. So in fact, we can even, now I'm writing here, what I mean is that V as observed in the fixed frame, V as observed in the small xy frame. I'm just dropping that actually, and omega cross R. So the observation with the fixed frame has two terms with regard to the rotating frame as it is, because in the rotating frame, the guy observer only sees that it is moving along x-axis. He doesn't have any other knowledge that it's actually also rotating with respect to the big xy frame. And then obviously this is the correction factor, which we have seen. And so in the vectorial form, what we have here, let's try to understand here. So as far as the velocities are concerned, we have a small vxy going along this. And what is the second term here? So we have to add vectorially omega cross r. So this is r to the origin, and we have to take a cross product with omega. So omega is coming out, assuming that it's counterclockwise. And then that vector, if you want to take a cross product with r, so if you rotate it like this one, so the cross product term will go in this direction. And since these two are perpendicular to each other, so this is magnitude is omega times r. Okay, so these are the two components vectorially, and so a vectorial sum here. So this is v big xy. So the big xy is the observation made in the rotating frame, and then a correction factor omega r. So together they will add. These are all vectors. Okay, so this is as far as the velocity is concerned. So now let's look at acceleration. So acceleration, the relationship is acceleration as observed in big xy frame is as observed in small xy frame, and this is omega r plus alpha cross r, or maybe I can even put for 2D, I can even put this, and omega k cross. So these are all vector quantities. So now let's look at, I'll draw it again here. So you are here, and this bead is moving with an acceleration here. Small xy, right? In the small xy frame, it is only having an acceleration along x-axis. And together with, we have minus omega square r. And that's nothing but this is r is this, and so omega square r is this. So this is omega square r. And together with, we have alpha k cross r. So if you have alpha, just like we did omega cross r, this is nothing but that. And we have, this is omega, sorry, alpha k cross r. And then we have this Coriolis component. So this is what we call as Coriolis component is 2 omega k cross vxy, and v is in this direction. And then if you take a cross product with this one, is nothing but you have so this is omega cross 2 omega, because these two omega and v are perpendicular to each other, so the magnitude just becomes 2 omega vxy. Okay, so okay, so these are the 4 components. This is the relative acceleration, and this is the omega square r. You know that this is omega square r is nothing but your kind of centripetal acceleration. The centripetal acceleration, that means that p is staying there, and then it is rotating with omega, so you have a centripetal acceleration. Now p is having rotating with alpha of the rotating frame, so you have alpha r. And then this is the last term, Coriolis component. Okay, so these 4 components, 1, 2, 3, 4, you have to add vectorially, and that is the total acceleration. So if you add, maybe this is the total. So this is the addition of all components. Okay, so all these components, these 3 are easy to understand. Only this one is the one, it is coming because the sliding velocity vxy, it's an interaction between the sliding velocity vxy and rotation of the rotating frame, that's omega. So I'll just show you what I showed. I explained it last time, but still let me repeat it all the same. So let me explain it. Why this has come is because what's happening here is that there is two things are happening in a small time. So this is, let us say, P and P prime in a small time. So this slider has gone from P to P prime in a small time. So that is, it has gone through a distance of delta R, can even be delta X, V delta T. So in this case, what's happening is, because of this change that has taken place of delta R, and what is the omega? So because of omega, what we have is the velocity here. So we have a tangential velocity, and here we have tangential velocity has increased by a magnitude. It has increased by omega times delta R, right? So since they're parallel, of course, but they have change in magnitude. So the acceleration here say some component here is how much is that? The change here is that so this is nothing but, so it comes out to be omega delta R by delta T, and it is nothing but omega times Vxy, right? So this is because the omega R component has increased by a small quantity because there is a change in the radial length. There is a change in the radial length. Okay, so this is one component of Coriolis. There is another component, and this is also because an interaction between V and omega. So here we have V like this, right? And what's happening because of omega, that means that it is going through so because of the omega, what's happening is that this X has now rotated through an X prime here, and in that process the velocity of the slider is what's happening to the velocity of the slider? So velocity of the slider is changing the direction, okay, Vxy. So if I just look at Vxy only, so Vxy has changed its direction by an angle of delta theta. So though the magnitude has not changed, but its direction has changed, so which is the change. So this is how much is that? So this is nothing but your V times delta theta. So this component is because your sliding velocity has changed its direction because of the rotation of the rotating frame. So that caused an acceleration, a change in the velocity. So what is the acceleration component? So the acceleration component is nothing but so this is acceleration. So this is nothing but this is again. So if you look at the directions of this one, so when delta theta is small, so then what happens is that this is perpendicular to Vxy itself, while the earlier one is perpendicular to the radial vector direction. So it is also in the same direction. So these two components add up to, So the total A here is nothing but A prime and A double prime, and both are same. This is the magnitude, and the direction is perpendicular to the R, perpendicular to the position vector R. Okay, so that is how the Coriolis component has arisen. It has arisen because something which is not observed, okay, in the small xy frame is that the V itself is changing. The tangential velocity is changing because of the presence of V, because there is a change in the radial distance. On the other hand, there's also another component that the sliding velocity V has changed its direction, so which gave the component, one component, A double prime. So these are the two things, and yeah, so that's how the Coriolis component has come, because the all other components are very easy to understand. For example, this is the centripetal acceleration, obviously, because you have not considered the rotation with respect to the xy frame, so there's a centripetal acceleration. And then there's a tangential acceleration, that's also easy to understand. There is a acceleration in the small xy frame, that's axy, that also is easy to understand. So, but this is the one which is easy to understand. Difficult to understand is because it is an interaction of omega and Vxy. So that's once you understand this, so that means that whenever you have an observation made in the rotating frame, and if you want to take the derivative of that, so one correction come, and then as far as the acceleration is concerned, so it is a second derivative of the observations made, and you will end up with the Coriolis component. Okay, so this is the second derivative. Okay, let us, I'll just again a small example, same thing, more to do with some numbers. So let us try to understand a small example. Maybe before I take up the example, so I want to compare this with another very simple approach which we had. In fact, if you recall, don't forget whatever we have done, you can forget. So in fact, before last week, we have done extensively on various frames. So we started with curvilinear coordinates, then we went to radial coordinates, then we went to polar, obviously, and then we went to spherical coordinates. Now we are coming to rotating frames. In fact, some of these, whatever problem which I just wrote it here for this problem, just come to this example just now. So I want to show you there are many ways of solving the problems, and then they're not at variance with each other. They're all same. So for example, here, this is what the bead which we are saying. So the bead can also be described, this can also be described so whatever analysis which we made in polar coordinate. So if you do it in polar coordinates, what is that? So polar coordinates is that R, and the position vector R is given as R, A, R. So we have ER and E theta, and obviously, so when theta moves, ER, E theta are changing. So we took the DER by DT. If you recall, it was nothing but omega times E theta, and D theta by DT, it was nothing but minus R omega times E, sorry, E theta, I mean ER. Okay, so that's what we did at that time. Remember? E theta, right? Theta dot or omega. This is what we did. Okay. So anyway, going all through that procedure. So we had velocity here is nothing but R ER. So it is nothing but, so if you want to get the velocity in the XY frame, is velocity is two components, is R dot, which is the radial velocity, and this is the theta, this is R theta dot or R omega theta dot. Okay. So these two will give you the total velocity, right? So, and then we went on to acceleration. We did one more thing. So wherein we have R double dot this is what we did, one more differentiation. This is what we got for the velocity in terms of ERE theta and RN theta as functions of time. So if you recall, this is R double dot. So what is R double dot? So if you, so can we make a parallel to, so what is R double dot? R double dot is nothing but how R is changing, the second derivative of that. So that means that R double dot in the direction of ER, right? Okay. Then R theta dot square with a negative. So it is again, it is, so this is R theta dot square. These are in the direction of ER. One is positive, one is negative. Then you have R theta double dot. So in the direction of E theta. And we also have another 2R dot theta dot. So what are these? Can we make a parallel of these four components for whatever rotating frames which we did, right? So it's, so if you see this R double dot is nothing but equivalent to our AXY. So it is nothing but the acceleration of the slider in the rotating frame. Then we have R theta dot square. So this is minus omega square R. And then we have R theta double dot. So this is nothing but your alpha omega. I'm sorry, alpha R. So theta double dot R. And then this is 2R dot theta dot. It's nothing but your Coriolis component. Okay. So there is a, so we are not at variance. So whatever do, you either do it in polar coordinates or in the rotating frames, they are absolutely in consonance, right? So you can, so if you understand these things, so that will be nice. Okay. So let me also do another, if not exactly a numerical example. I will just go one more step and try to bring in curvilinear coordinates. Let's just do that. So let us say that I have so this is, say, another example. So many examples. Okay, so now let's assume that I have a cardboard attached to small xy, and then I have a small slot cut in this one, the cardboard. Okay, so I hope you can. So if you want, I'll put everything in yellow. So let us say it is a curved path, and then you have a center C here with some radius of curvature rho. So the center of curvature is C, and I'm sorry, yeah, and rho is the radius of curvature. Let's assume that we are here, we have a point P here, and P is moving in the slot which has center C and radius of curvature, and then the whole cardboard is rotating with a omega and alpha. So now if you want to find out the relationship between velocities, so we can do so. It's very simple. So for that, so velocity relationship is so let us say let's say this one. So this is your R, right? From O to P is R. So let's try to understand these things. So the components here are the velocity Vxy. So the velocity Vxy is along the tangent, right? So in the small frame. So we can even say that it is V times what is the direction? So this is Et and this is En. Et and En. Et is the tangential and N is the normal. So that means that this is along Et. So this is the velocity. So now, so that is the velocity. And what about this one? So this is, what is this omega cross R? So it is omega times R here. So R, we are combining really all coordinates here. So R, this is R, right? So you can say that what is the, so if you extend this one, so the direction of R is along the extended direction. And if you take a cross product with K, so you have a omega like this, and then you have an R like this one. So what is this component? So this component is perpendicular to this. So this one, omega cross R. So this is omega, magnitude is omega R, and it is in the direction. Well, in your convention, so you can even say that if you call this as the convention by ER and this is by E theta, so we can say that it's omega R E theta. So we are combining several unit vectors. Absolutely, there's nothing wrong. So as long as you understand what is E theta and what is E theta, so it's a matter of our convenience, right? So which ET or ER, whatever, as long as we know how they are measured with respect to what frame. So this is what V is. Let's try to understand A. So acceleration of AXY. So as observed in small xy frame, and minus omega square R plus alpha K cross R Okay, so AXY, what is AXY? Can you tell me what is AXY? AXY, acceleration of the particle as it moves in the small frame without any knowledge that you are rotating. You don't have any knowledge that it is rotating. So what all it's doing, as far as this, it is going in a slot. Okay. So if it is going in a slot and like this, and we have a P here, what is its acceleration? So it's moving P, and it's, as far as its acceleration is concerned, then we have to draw our knowledge of curvilinear coordinates. So in the curvilinear coordinates, a particle moving along a curved path will have two components of acceleration. One is v square by rho. So what is v square by rho? That is, this is an, and you have an, and we have at. So as far as axy is concerned, we have an and at, and an is v square by rho, and in particular, if you want the direction, en. And what is at? So the at is the v dot times e. Okay. So this is an and at, and this is, if you combine this, so this is small x. So the small xy has two components, an and at. Okay. So this is that one. And then we have minus omega square r. And how is the minus omega square r? So I think the other components you will be able to understand. Going to be a little messy, but let me so this is at and an, and then we have minus omega square r. So this is, let me call them as components. Let's see. So we have an at. So we have this is nothing but a1, and then we have omega square r here. This is a2, and then we have the tangential. So this is a3. I'm sorry, a2, a3. Then what is a4? A4 is a Coriolis component. So how is that? Can you tell me what is the direction of this Coriolis component? So Coriolis component is coming off 2 omega cross vxy. So that is nothing but vxy is along the tangent, right? So vxy, observe that vxy so vxy, as I said, so it's v times et, right? So it is along this direction. So this is v, and then you have to take a cross product with omega. So you have omega here, and then you have to take a et there, and so that means that what it will be? It will be perpendicular to this one. So it's actually like this. So this is A4. So its magnitude is 2 omega, the tangential velocity. So understand now? So there are so many components, but not all in the direction of R or perpendicular to R. So it all depends upon how the velocities and accelerations in the small xy frame change. Yeah, so I hope you have understood. So in a simple slot along x-axis, and then in a complex slot which is curved, and then what is the various accelerations here with respect to small xy frame, and a A2 component here, A3 component, and the Coriolis component A4. So once you have understood all these things, so putting them in terms of vectors, okay, now I qualitatively explain. So we can also give the vectorial notation for each one of them. Okay, I will take up a small numerical example tomorrow, 2 examples, and again I will explain all these things with respect to numerical example. Okay, I think I should stop here. So please go through it carefully, each component, what is its magnitude and what is its direction. So you should try to understand. Once you understand these things, so converting the vectors into components. So for example, here I have used 2 types of coordinates here. One is ENET and another is in perpendicular to x and y. So right, so that also, or even ER, E theta. So ER, E theta can be converted to ENET. All of them can be converted to the I and j in the small xy frame, all of them. So it's only a matter of transformation. Okay, at that stage, once you have this, so converting from one frame to another at some angle is only a matter of transformation. Okay, so I'll stop here.